So we are in, this is section 6.3, and we're going to talk about vectors, and for now we're just in two dimensions, so we're going to say vectors in the plane. Later on in the semester we'll talk about vectors in space, three-dimensional vectors. So part of what we're going to do today is talk about what a vector is, and then we'll talk about a few of the things that we do with vectors. So vector, we want to know what it is. A vector is something that has a direction and a magnitude. So everything we've talked about so far, all the numbers, all the functions, we just end up with one number. So we say that x equals 5. Well, with a vector we need to know the direction and the magnitude. It's that direction and it's 5 units in that direction. So some examples of things that we need vectors to talk about. Position. So we're in that direction 20 yards. That's different than that direction 20 yards. So position is a vector. Velocity. We're going this direction at 20 miles an hour. Going that direction 20 miles an hour is different than going this direction 20 miles an hour. Force. 20 pounds this way is different than 20 pounds that way. So those are some examples of vectors. We need to know the direction to have all the information that we need. We think of vectors, the way we think of them, the way we visualize them, is as a directed line segment, which is really a fancy way of saying an arrow. So let's draw a picture of a vector. Do it in red here. Here's a vector. It's going in a specific direction. It has a specific length. So we're going to name some pieces here. If it starts off here at point P, we call that the initial point. And if it goes to point Q, we call this the terminal point. And we would name this vector PQ, and we put this little half arrow over the top. We could also name it vector, we could also call it vector V. And I put a little tail on my V because my V's and my U's end up looking the same. So we can call this vector PQ, vector V. When we've used the 2 points, the initial point and the terminal point, it starts at point P and ends at point Q. In your book, they use bold letters for vectors. So in print, you'll see a bold letter. A bold letter means a vector. When we write them out by hand, we use the little arrows. And sometimes you'll also see like a capital letter with a double line along the side, and that would be vector A. Sometimes you'll see it that way as well. Mostly you'll see the bold or you'll see the little arrow. The magnitude of the vector, when we talk about the magnitude is the length of the vector. So if we have a vector and it starts at point P and a point Q, how would we find the length of that vector? What would we do to find the length? Distance formula. We find the length, we find the magnitude by using the distance formula. The symbol that we use for the magnitude or the length of a vector is we put double bars around the vector. So when we write that symbol, that's the magnitude of V. And I learned it, when I learned vectors, we only used a single set of bars, so it looked like the absolute value. It means the same thing. One set of bars, two set of bars mean the same thing. This is a little less messy to write, so a lot of times I end up writing this. It means the same thing as this. So if you see those two, they mean the same thing. For the magnitude, length of the vector, we use the distance formula to find the length. Vectors are equal. If they have the same magnitude and same direction. So it doesn't matter where it's located, as long as the vector has the same magnitude and direction as some other vector, we call them equivalent. They don't have to be on top of each other, they just have to have the same magnitude and same direction. That's how we tell if vectors are equal. So let's look at an example. Let's figure out if we have two equal vectors here. So we have a vector from, so V is from 0, 0 to 4, 5. And the vector U is from 2, 3 to 6, 8. And we want to know, is U equal to V? So we have two pieces of information we need to figure out. Are they the same length? And are they in the same direction? So how are we going to figure out their length? The magnitude of V is, how are we going to figure this out? Distance formula. So distance formula, we get 4 squared plus 5 squared, which is the square root of 41. And the magnitude, or the length of U, use the distance formula, 6 minus 2, 4. 8 minus 3 is 5. And we get the square root of 41. So they have the same magnitude, they have the same length. Now we need to know if they're pointing in the same direction. How can we figure out if these two vectors are pointing in the same direction? What's that? We could use sine and cosine. We'll talk about doing sine and cosine a little more tomorrow. So if you were worried that we were leaving trigonometry behind, we weren't going to talk about trigonometry. Vectors and trigonometry are very close siblings. So we get to use sines and cosines and tangents and all of that nice stuff with vectors. How could we do? So we could use sines and cosines. How could we do it without? In this particular case, how could we do it without sines and cosines? We could graph it. So thinking about graphing, what would tell us if two segments were going in the same direction if we graphed it? Their slope. We could look at their slope. So if their slopes are the same, they're going to be going in the same direction. So the slope. And the slope of a segment is related to what trig function? figure that one out right at the beginning of the semester? Keep that in the back of your head. We'll talk about that one later. So slope of vector v. What's going to be the slope of v? How do we figure out the slope of this segment between these 2 points? y1 minus y2, or y2 minus y1. 5 minus 0 over 4 minus 0. Slope is 5/4. Slope of u, 8 minus 3, 5. 6 minus 2 is 4. Same magnitude, same slope, so the vectors are equal. All right, nice and easy. Not too difficult to figure out. Questions on that example? All right. Let's draw another picture. And just like we did when we dealt with angles, it's nice if we can put our vector with the initial point at the origin. So if we're on the plane here, x and y, and we put our vector on there, and I'm going to call this vector v. And I'm going to call the initial point, now that we're on this coordinate system, the initial point is 0, 0, and the terminal point is v1, v2. So this is our x and this is our y. When we put a vector with its initial point on the origin, we call this standard position. So this is our standard position for a vector. And when we're in standard position, our vector, we can write v, and we use these angle brackets, v1, v2. v1 tells us how far we go in the x direction, v2 tells us how far we go in the y direction. So when we're in standard position, this is how we can write our vector. This is called component form. So when we write our vector in component form, it's telling us in the plane how far do we go in the x direction, how far do we go in the y direction. That's what our components tell us. X component, y component. If our vector is not in standard position, if v is between 2 points, between x1, y1, and x2, y2, then our component form, we can write v. We just subtract the components. x2 minus x1, that tells us how far we go in the x direction to get from here to here, and y2 minus y1. So that tells us how far we go in the y direction to get from here to here. So that's going to be the component form of our vector if it goes between 2 points, if our initial point isn't at the origin. And the magnitude of a vector in standard position we just use the distance formula, and if we're in standard position, our initial point is 0, 0, so this should be the magnitude of v is just the square root of v1 squared plus v2 squared. I'm trying to need to work a little harder to make my v's look like v's and not like r's. So if we're in standard position, our magnitude is we just square each component and add them together and take the square root. So questions so far? So we have this thing that has a magnitude and a direction. In order for vectors to be equal, they have to have the same magnitude, same direction. Our standard position is when our initial point is at the origin, and our component form tells us how far we go in the x direction, how far we go in the y direction. So a couple of other things about magnitudes, and then we're going to start doing some things with vectors. So if our magnitude is 1, the magnitude of our vector is 1, then we call v is a unit vector. And unit vectors are going to be very important in what we do later on with vectors. And as you move forward, if you do more math, unit vectors are really important quantities when we talk about vectors. So if our magnitude is 1, we call v a unit vector, because our length is 1 unit. If our magnitude is 0, we call v the 0 vector. And the 0 vector is different than the number 0 because we're saying that the 0 vector is a vector that has no magnitude. So we're going 0 miles an hour in this direction. So the 0 vector is different than the number 0. So if our magnitude is 0, we call it the 0 vector. All right, so what do I want to do next? I want you guys to tell me. So we have a vector. Our vector is from 2, -4 to 5, 7. We want the component form and the magnitude. So we'll figure out the component form and the magnitude, and then we'll write it down. So we have a component form. What's going to be our component form of this vector? 311. And we use the angle brackets here. So 5 minus 2, 3, 7 minus -4 is 11. And our magnitude, nice and easy to calculate from here. Square root of, what do we come up with? 130. 3 squared plus 11 squared. So that's our magnitude and our component form of our vector. And this tells us to go from 2, -4 to 5, 7. We move 3 units in the x direction and 11 units in the y direction. So that tells us our direction, and these tell us our magnitude. That's how we find our magnitude. Questions on how we did that? All right. Now we want to do things with vectors. We know what they are. We know how to find the component form. We want to do things with them. So let's talk about how we do things. Vector operations. So like I said, nothing really complicated today. Just a lot of things, a lot of little pieces, little details about vectors, so we can actually start doing things with them. Then we start doing things when they get more interesting. All right, so for our vector operations, we're going to say that U is our vector U1, U2. V is a vector V1, V2, and K is a real number. And when we're talking about vectors, rather than calling it a number, we call real numbers, we call them scalars. So we call real numbers scalars when we're dealing with vectors. So we have vectors that have a direction and magnitude. We have a scalar, which is just a number. To add vectors, all we're going to do is add their components. That's all we need to do to add 2 vectors. And what we're doing here geometrically, if we draw a picture of what we're doing when we add them, we add 2 vectors by putting them head to tail. So if this is a graph and these are our 2 vectors, if we wanted to add U and V, here would be U, there would be V, and U plus V would be the vector we get by connecting the initial point here to the terminal point. And some people think about this as drawing a little parallelogram, a little box. So this is parallel here, and that's parallel there, and U plus V is the diagonal of that parallelogram. So that's another way you can think about it. So we add them if we're drawing a picture, we add head to tail. And the head of the vector is where our arrow is. So we add them head to tail. All we're doing is adding the components. When we add them together, we go a total of this number of units in the x direction, a total of that number of units in the y direction. If we multiply a vector by a scalar, k times u, we just multiply each component by the scale, by that number. And what do you think multiplying a vector by a number does? What is that going to do to the vector? What is it? Someone said it? makes it longer. Or if we're multiplying by a fraction, it would make it shorter. So we're just multiplying the vector by the length of the vector by the scalar. So this would be, if k was 2, and we said 2 times the vector u, we would get a vector twice as long as the original vector. Still in the same direction, just be twice as long. So we're just making it longer, making it shorter if k is a fraction. So just to kind of preview what we're going to talk about next, what would multiplying it by negative, say negative 1, what would that do to it? Reflect it, it would turn it around. It would change the direction. And that's how we're going to talk about subtraction. So to add our vectors, we add the components. To multiply by a scalar, we multiply each component by a scalar. To subtract, we're going to think about flipping one of them around. So we're going to say negative u is negative u1, negative u2. So if I were going to do v minus u, I could think of that as saying I'm going to do v plus negative u, and that's the same thing as subtracting their components. v1 minus u1, v2 minus u2. So to subtract a vector, we're just subtracting their two components. And graphically, what we're doing when we subtract, if I draw a picture here, so you have a visual of what we're talking about. When we subtract them tail to tail. So if this is v, and that's u, this vector is going to be v minus u. And we can visualize that by thinking of flipping u around, turning it the other opposite direction. So the green vector is minus u. And now I have these two vectors head to tail, and this is v minus u. So we subtract tail to tail, if we're drawing pictures. And what I always think about with these pictures is we're starting at the initial point, and we're ending at the final place that we get to. So our vector goes from the starting point to the ending point. That's how I always think about them. But really, for the most part, all we're going to be worried about is their components. We subtract their components when we're subtracting. Add their components when we add. Multiply each component by a scalar when we by a number when we multiply by a scalar. That's really all we're doing. So questions here on our operations. No questions on operations? Okay. Last thing I want to do is talk about some properties of addition and scalar multiplication. Just how different things that we can do, different ways we can work with the vectors. I'm not going to spend a lot of time with these. They're a lot like we've talked about or we've used basically since elementary school for adding and subtracting numbers. We're just adding and subtracting vectors, and we're multiplying by a scalar. things get more interesting when we start multiplying vectors by each other. Some interesting things happen. So I'm just going to list some properties, and then we'll be done. And our properties are for vector addition and scalar multiplication. We'll have other properties for other things that we do. So for these, we're saying U, V, and W are vectors, and C and D are scalars. So the first property, it doesn't matter which order we add vectors. So U plus V equals V plus U. We'll get to, a little later, we'll get to a way that we work with vectors where the order that we do things does matter. So we can't switch them around. In this case it does. And this is our commutative property, just to give it a name. We're not going to talk about it a lot, talk about the names, but this is commutative property. It's an important property. U plus V plus W. Doesn't matter how we group these things when we add them. That's the same as U plus V plus W. So we can group them together in different orders, and when we add them, and it still comes out the same. So this is our associative property. If we add the zero vector to any vector, we just get the vector back. So the zero vector is our additive, what we call our additive identity. What do you think we get when we add a vector and its opposite? Zero vector. So if we add U and negative U together, we get the zero vector back out. So we have an additive inverse. If we're multiplying by scalars, it doesn't matter how we do the multiplication. We can multiply the scalars together first, multiply by the vector, or multiply them in this way. If we're adding the two scalars together and multiplying by a vector, we can distribute the vector. Almost done. So if we're adding two vectors and multiplying by a scalar, we can distribute the scalar. One times any vector is just the vector itself. 0 times any vector gives us the zero vector. And finally, the magnitude of a scalar times a vector is just the absolute value of the scalar times the magnitude of the vector. So, pretty intuitive based on how we've been working with numbers. Basically the same way we've been working with numbers. The reason we're listing these out is there are some things that we'll do in the future that don't have all of these, that don't necessarily have all of these properties, where the order that you do the operations matters, where it changes things. So we want to make sure we're careful and we know exactly how these properties work. So our bottom line today, vector, magnitude, and direction. We know what a standard position is. We know how to find the component form of a vector. We You know how to add and subtract vectors. And multiply by a scalar. So any questions today? All of our homework has to do with talking about the component form, finding the magnitudes, and adding and subtracting. So it should be a pretty easy day. So our homework. There you go.